In this video, we are going to talk about how to graph logarithmic equations. And by the end of the video, you are going to easily be able to navigate and graph the equations listed on your screen, whether it is just the basic parent function listed here, or whether we introduce negative signs or constants inside the parentheses, and or fractions along with the x, constant in the parentheses, and constants outside of the parentheses. Notice that logarithm is spelt with an I, unlike the word rhythm. And my mnemonic for remembering how to spell the word rhythm is rhythm helps your two hips move. But as mentioned, logarithm in terms of math is spelt with an I. Ladies and gentlemen, that logarithmic functions and exponential functions are inverses of one another. When you look at a log function, they feature a vertical asymptote, and part of the graph is going to hug that vertical asymptote and then head off in a certain direction. With an exponential equation, you have a horizontal asymptote. And here, the graph is going to hug this horizontal asymptote and head elsewhere, or if it's a decay problem, you will see the graph heading towards the horizontal asymptote. The thing that's common, though, between a logarithm and an exponential equation is that they both have a base. So let's focus on that base for a second and talk about the restrictions on a base. It turns out they're the same for logarithmic and exponential equations. So here we go. For a logarithm and an exponential equation, the base is not allowed to be negative and it can't be 0 or 1. A fraction is okay. Red means it cannot be negative. Open circle means it can't be 0. Open circle on the 1 means it can't be 1, but it's okay to be between 0 and 1, namely a fraction, and it of course is okay to be greater than 1. When you look at the logarithm in more detail, as mentioned, the base of the logarithm has to be positive. It can't equal 1. It cannot equal 0. Can't be negative. But the argument, however, is a little bit more lenient. It's similar in that it must be positive. It can't equal 0. It can't be negative, but it's okay for that argument to equal 1. So let's look at some examples. Okay, here's the summary statement down here in red, that the argument is a little bit more lenient. Okay? First example, this is not legal because you have 0 in the argument. Okay, so this is a red X right there. Here, we have 0 in the base, red X. Next one, negative as a base. No good. Next one, 1 as a base. Not good. Here, 1 in the argument. That is okay. Again, the argument is a little less restrictive. It's a little more lenient in that it allows for 1. Final one, we see a negative in the argument. Therefore, this is a red X. So if you want to go ahead and take a screenshot of this, I believe that would be advisable. Let's move on now to graphing log functions, and let's start with parent functions. A parent function is similar to what we have here, y equals log of x. Notice there's no transformations here. There's no negative signs. There's no coefficient with the x. There's no constant within the parentheses, and there's no constant outside of the parentheses. It turns out these parent functions can be easily graphed by recognizing two things. One, that they all have a vertical asymptote at x equals 0, otherwise known as the y-axis. And secondly, they all have 3 common points, and here they are. 1 over the base, comma, negative 1, 1, comma, 0, and the base, comma, 1. So if we consider y equals log of x, we know that there's an implicit 10 here. And if we plot the vertical asymptote at x equals 0, namely the y-axis, and we plot our 3 points, here we have 1 over the base, comma, negative 1, 1 comma 0, and the base comma 1, we use the fact that all log functions will hug the vertical asymptote and then go through these points and continue on like so. Now, I want you to notice something. Notice that this graph heads towards the first quadrant. And recall, in the first quadrant, both the x value and the y value are positive. Okay, so here in this first quadrant, x is positive and y is positive. And I want you to look at the parent function. Notice that this has a positive sign and this has a positive sign. And as you'll see, we can use this intuition based on the sign associated with the x value and the sign in front of the log to determine which of the 4 quadrants is going to take this graph. In other words, based on these signs, we'll be able to determine towards which quadrant the log function is heading. Let's look at another parent function. Here we have y equals log to the base 5 of x. Again, no transformations. Okay, we know that this graph is going to have a vertical asymptote at x equals 0. And then there's going to be 3 points. The first point is going to be 1 over the base, comma -1. The second point is going to be 1, comma 0. And the third point is going to be the base, comma 1. So let's plot those points. We're going to have -1/5, -1, 1, comma 0, and 5, comma 1. So here we go, something like this. Again, positive in front, positive with the x, heading towards the first quadrant. Okay, let's now move on to graphing logarithmic functions with transformations. So here we have the parent function, y equals log of x, and now we are applying a transformation. As you can see, there's now a constant within the parentheses of the argument. There are 2 ways to do this. You can plot points, which is the method I prefer, or you can plot the parent function and apply transformations. I'm going to show you both methods just in case your teacher requires you to learn how to use this second method. But again, my preference is to plot points. So here's how you plot points. You set the argument to 3 things. First, you set it to 0, then you set it to 1, then you set it to the base. You then solve for x. When you set it to 0 and solve for x, it provides the vertical asymptote. Here, we're going to solve for x, and then we're going to plug x into this function to get our y value, and we're going to plot these 2 points. And the asymptote plus 2 points is all you need to sketch this graph. So here we go. We first set the argument equal to 0, 1, and the base, and then we solve for x. When we set it to 0 and we solve for x, we get x equals positive 2. That's going to be our vertical asymptote. Here, we set it to 1. We solve for x. We get x equals 3. We then take x equals 3 and plug it into the original equation and solve for y, and we end up with the log of 1, which is 0. So our y value is 0, and our x value is 3. And that's going to be our first point right here. Our next point we obtain by setting the argument equal to the base. Remember, the base of this log function is 10. Set it to 10, solve for x, we get 12. We then take x equals 12 and plug it in to the original function to get our y value. 12 minus 2 is 10. When you have the base matching the argument, these cancel out and you get the exponent. In this case, the exponent is 1. So our y value is 1. Again, here's our x value, and now we solve for the y value of 1, and that now is our second point. So to review, here are the particulars. We have a vertical asymptote at x equals 2. That was obtained by setting the argument into 0. Now we have 2 points, 3, 0, and 12, 1. Let's first plot our vertical asymptote. Our first point is going to be 3, 0. Our second point is going to be 12, 1. We know our intuition, as we talked about previously, of this function. There's a positive sign here. There's a positive sign associated with that x. Where are the y value and x value positive? None other than the first quadrant. So this graph is going to hug the vertical asymptote, and it's going to come through these 2 points and head continuously into the first quadrant. In our next example, we see a relatively similar problem. We have a transformation with a constant inside the argument. We're going to take our argument and we're going to set it equal to 3 things: 0, 1, and the base. The base is 10. Here, we're going to get x equals -3. This is going to be our vertical asymptote. Here, we're going to get x equals -2. And here, we're going to get x equals 7. Okay, let's now plug in x equals -2 into the original function. We're going to have log of -2 plus 3. That's going to equal log of 1, and that's going to equal 0. So our first point is going to be x equals -2, y equals 0. Over here, we're going to plug in 7 into the original equation. Don't forget, it has the base 10. We're going to have log base 10 of 10, and that's going to give us 1. Our second point, therefore, is going to be 7, 1. Now let's go ahead and graph it. Our vertical asymptote is going to be at x equals -3. Our first point is going to be -2, 0. Our second point is going to be 7, 1. So this graph is going to look something like this. Again, the original function has a positive associated with the y, a positive associated to the x, so it is going to head towards the first quadrant. In our next example, we have y equals negative log of -x. What does our intuition tell us? See that negative sign? That's going to be associated with the y value. This is going to be associated with the x value. If you look at our quadrants, where are the x value and the y value both negative? None other than the third quadrant. So ultimately, I'm expecting this graph to head towards the third quadrant. But let's go ahead and prove it. First thing we do is we're going to set our argument to 3 things. We're going to set it equal to 0. That's going to give us our vertical asymptote. We're going to set the argument equal to 1, and we're going to set the argument equal to the base. If we solve for x, our vertical asymptote is going to be at x equals 0. Here we're going to solve for x, and we're going to get x equals -1, and then we're going to get x equals -10. We're going to we are going to take this and plug it in for x to get our y value. That's going to be log of 1, which is going to equal 0. So our first point is going to be x equals -1, y equals 0. We're going to get our second point by plugging in -10 into the equation. Don't forget that negative in front. When you have the base equal the argument, it becomes the exponent, which is 1, and the negative out front makes it a -1. So here our second point is going to be -10, -10, comma, -1. Okay, let's go ahead and graph it. We have a vertical asymptote at x equals 0, otherwise known as the y-axis. Our first point is -1, 0. Our second point is going to be negative 10, negative 1. So here, the graph is going to hug the vertical asymptote and then approach the third quadrant just as we predicted. Let's now consider this function, which for the first time features the natural log. And as you'll see, the plotting points method works swimmingly with natural log. First, what's our intuition? We have a negative associated out front. That's going to be associated with the y value. And we have a positive sign located inside the argument associated with the x. So our intuition on this graph is that it's going to head towards the region where y is negative and x is positive. So that is going to be quadrant 4. So let's see if that pans out. We're going to set our argument to 3 things. We're going to set it equal to 0. We're going to set it equal to 1. And we're going to set it equal to the base, which in this case, as you know, is e. We're going to solve for x here and get x equals negative 3. That is going to be our vertical asymptote. Here, when we solve for x, we get x equals negative 2. We're now going to plug in negative 2 for x. So we have negative natural log, negative 2 plus 3. That's equals negative natural log, which is to the base e of 1. And that's going to be negative 0 or 0. So our first point is going to be x equals negative 2 and y equals 0. Here, when we solve for x, we're going to get x equals e minus 3. We're going to plug in e minus 3 into our original equation. We're going to get y equals negative natural log of e minus 3 plus 3. That's going to equal negative ln of e, base e. These cancel out, give us the exponent, which is 1. Here, y is going to equal negative 1. So our second point is going to be x equals e minus 3, comma, negative 1. And we can clarify e minus 3 by saying e is 2.7, roughly minus 3, negative 1. So that is going to be negative 0.3, comma, negative 1. Okay, so we have our vertical asymptote. We have our 2 points. Our vertical asymptote is x equals negative 3. Our first point is negative 2, comma 0, which will put us right here. Our second point is negative 0.3, negative 1. So we have a graph that hugs the vertical asymptote and heads towards the fourth quadrant, which is what our intuition told us, because recall the y value was negative, the x value positive. Next, we have a log with a unique base of 3. We have a constant within the argument, and then we have a constant outside the argument. Our intuition on this one is that we have a positive value associated with the y, a positive with the x. So we anticipate that this graph is going to head towards the first quadrant. First thing we do, x minus 3 equals 0, x minus 3 equals 1, and x minus 3 equals the base, which in this case is 3. Solve for x here. Our vertical asymptote is going to be at x equals positive 3. Here, when we solve for x, we get x equals 4. And here we have x equals 6. Let's plug this in to the original equation. We have y equals log to the base 3 of 4 minus 3 minus 2. This is going to become 1, which makes this 0, and therefore our y value is going to be negative 2. Our first point is going to be x equals 4, y equals negative 2. Let's plug in x equals 6, log to the base 3 of 6 minus 3 minus 2. log base 3 of 3 minus 2. This is going to become 1 minus 2 equals negative 1. So our second point is x equals 6, y equals negative 1. Let's go ahead and plot our function. Vertical asymptote is at x equals positive 3. Our first point is going to be 4, negative 2. Our second point is going to be 6, negative 1. Therefore, our graph is going to hug the vertical asymptote, go through these 2 points, and indeed head towards the first quadrant as predicted. Let's do one more function using the plotting point technique. So here we have the natural log, negative 1/2 x minus 3 plus 1. First, the intuition. You have a positive sign associated out here. That's going to be associated with the y value. And within the argument, we have a negative sign associated with the x. So in our quadrants, where is the y value positive and the x value negative? That's going to be quadrant 2. So we're expecting something like this. First thing we do is we set the argument to 0 to get our vertical asymptote. We then set the argument equal to 1. And finally, we set the argument equal to the base, which in this case is e because we're dealing with natural logs. We're going to have negative 1/2 x equals 3. And if I multiply both sides by the reciprocal of negative 1/2, that's going to be multiplying this side by negative 2 over 1. I'm going to end up with x equals negative 6, and that is our vertical asymptote. Next, we're going to say that negative 1/2 x equals positive 4. Again, we're going to multiply both sides of the equation by negative 2 over 1. Let's do that. Negative 2 over 1. 2's cancel, the 1's cancel, and now you have x equals 4 times negative 2 over 1, which is negative 8. We are then going to plug negative 8 into our original equation, which is negative 1/2 x minus 3 plus 1. So negative 8 is going to go into the equation to determine our y value. So we're going to get natural log of negative 1/2 times 8 minus 3 plus 1. Natural log of negative 4, positive 4 minus 3 plus 1. Natural log of 1 plus 1. The log of 1 is always 0. Therefore, our first point is going to be negative 8, comma, positive 1. Let's find our second point. We're going to have negative 1/2 x equals e plus 3. We're going to multiply both sides of the equation by negative 2. And we're going to end up with negative 2e minus 6 as our x value. We are now going to plug in this x value into the original equation to get our y value. Okay, so we're going to get the natural log of, this is going to be e plus 3 minus 3 plus 1. Natural log of e to the base e plus 1. This becomes 1, and we get 2. As you can see, folks, this system of setting the argument into 1 and setting the argument into the base is designed to get easy integers. Now we have the y value of 2. The x value is negative 2e minus 6. So let's go ahead and evaluate this. E is going to be about 2.7. So negative 2 times 2.7 is going to be negative 5.4 minus 6 comma 2. So this is negative 11.4 comma 2. Let's call this negative 11.5 comma 2. Okay, so what do we have? What are our particulars? We have 1 point is negative 8 comma positive 1. Our second point is negative 11.5 comma positive 2. And our vertical asymptote equals negative 6. Again, we expect this graph to head towards the second quadrant. Okay, here's our vertical asymptote at negative 6. Our first point is going to be negative 8 comma positive 1. Our second point is going to be negative 11.5 comma 2. So we're going to have something like this, heading as predicted towards quadrant 2. Let's go ahead and just quickly look at the graphing calculator. I went ahead and did this ahead of time. Here's our function, natural log negative 1/2 x minus 3 plus 1. Here's our origin. Here's our vertical asymptote, x equals negative 6. Here's our first point, negative 8 comma 1. Here's our second point, negative 11.5 comma 2. As I mentioned earlier in the video, there are two ways to graph log equations. One is to plot points, which is what we have focused on so far in this video, but you can also use transformations. So let's go ahead and review how do we use transformations to graph an equation such as that listed here. Well, this is going to involve using the parent function, which is going to have a base, and transforming it based on what these constants are within the argument, outside the argument, and what the coefficients are located both in front of the log and in front of the argument. What we're going to do, folks, is we're going to use the original points of the parent function, which, recall again from earlier in the video, all parent functions have these points in common. 1 over the base comma negative 1, 1 comma 0, the base comma 1, and they all have a vertical asymptote at x equals 0. All of these points are going to be moved, shifted, perhaps reflected if there's negative signs involved, and we're going to get new points, which is indicated by the prime. This is the formula that we're going to use, and I suggest you go ahead and take a screenshot if you can. And I want to point out some aspects of this formula. Okay, so that will be your first screenshot. And then the second screenshot would be here, which shows exactly how we get to the new points. So let's go back to this equation, this transformation equation. And these letters are going to correspond to the coefficients and constants that I mentioned above. Now I want you to notice two things. First, that the coefficient of the x has to be a 1. So if you start out with, let's say, a 1/2 here in front of the x, you need to pull that out and create a b value, because you can't do transformations unless and until that x coordinate is 1. The other thing I want to point out is the difference between the negative sign here associated with this c value and the positive sign associated with the d value. And whenever you see a negative value in a generic equation, you do the opposite. When you see a positive sign in the generic equation, you take whatever you see. Okay, what do I mean by that? Okay, let's look at some familiar equations, like the equation, the y-intercept version of a line. As you know, it's y equals positive mx plus b. So if I asked you what the slope was of this real world equation, you would tell me it's exactly what you see, which is a plus 3. That's because the generic equation has a positive in front of the m. So the m value would be positive 3. If I asked you what the y-intercept is, you would tell me that it's negative 2. That is because this positive sign in the generic equation means you take exactly what you see. Now, let's compare and contrast that scenario with this generic equation, which is the vertex equation of a parabola. So here, recall that the h and the k represent the coordinates of the vertex. But because of this minus sign, when we take the x coordinate of the vertex in this real-world example, we are going to take this positive 3, and as we bring it into our answer, we are going to flip the sign. And why do we flip the sign? Because of that negative sign. That means do the opposite. Now, for the y value of the vertex, because of that plus sign associated with the k, we are going to take what we see in the real-world equation and we're going to use exactly as is. So when we do these transformations, as you'll see, this is how we're going to get our new x value, indicated by the x prime. We're going to take the original x, we're going to divide it by this b value, and then we're going to either add or subtract based on what we see in the argument, and we're going to do the exact opposite, just like we did with the vertex equation. When we get our new y value, however, we're going to multiply the original y value by the a coefficient, which is out here, and we are simply going to add or subtract exactly what we see. Let's now go ahead and graph this logarithmic function. And previously I had presented a screen and suggested a screenshot, but I think this is a better one to take. So if you have a moment, this shows the formulas that we're going to use. When we look at this equation, we recognize that the parent function is going to be y equals log to the base 3 of x. So this parent function is going to have the following 3 points. It's going to have 1 over the base, comma, negative 1. It's going to have 1, comma, 0. And it's going to have the base, comma, 1. We are now going to transform the points using the formulas that we just reviewed. So our new x value is going to be 1/3 divided by b. Our b value here is positive 1. And then, because the formula says to use negative c, we're going to take the opposite of what we see here in this argument, and we are going to add 3. So our new x value is going to be 3 1/3. Our y value, we're going to take the original y value, which is negative 1. We're going to multiply that times our a value, which is positive 1 here. And then we are going to apply exactly what we see as our d value. And that's because the new y value uses positive d in the generic formula. So we're going to have exactly what we see. So we're going to have negative 1 minus 2, or negative 3. For our next point, 1, comma, 0, we're going to take our original x, divide it by 1, apply the opposite, and our new x value is going to be 4. For our y value, we're going to take 0, multiply that times 1, and subtract 2, so our new y value is negative 2. Finally, our 0.31, our original x value is 3. We'll divide that by 1, we'll add 3, and our new x coordinate is going to be 6. For our y coordinate, we're going to take the original y value, which is 1, multiply it by 1, and subtract 2. Our new y value is going to be negative 2. With respect to the vertical asymptote, our original vertical asymptote is x equals 0. So we're going to take that, divide it by 1, apply the opposite of what we see in that argument. So our new vertical asymptote is going to be at x equals positive 3. Let's go ahead, folks, and graph this now. Actually, I forgot to do the intuition. The intuition says that there's a positive sign out front, a positive sign associated with that x. So I anticipate this graph is going to head towards the first quadrant. Here is our vertical asymptote at x equals positive 3. Our first point is going to be 3 1/3 and negative 3. Our next point is going to be 4 minus 2. And finally, 6, comma, negative 1. So this graph is going to hug the vertical asymptote, go through the points, and indeed head towards quadrant 1. Let's now graph this logarithmic equation using transformations. So the first thing you notice is that the coefficient of x is not 1. So we're going to have to pull this 1/3 outside of the parentheses to create our b value and our x coordinate of 1, and then make an adjustment to this constant so that we have the correct formula. So let's go ahead and say we have y equals 3 log. We're going to pull out the 1/3 as our b value. The x stays the same, and then that 1 changes to a 3. Now, I always like to go back and double check my work in this scenario. So I'm going to go ahead and set this up and redistribute that 1/3 and just make sure that I did this correctly. All right, and indeed that matches our original equation, 1/3 x minus 1. Okay, so here's the equation we are going to be working with in terms of our a, b, c, and d values. So let's go ahead and document those. Our a value is going to be 3. Our b value is going to be 1/3. Our c value, we're going to take this and take the opposite of it. This is what we are going to work with, plus 3. And our d value stays the same as plus 2. And recall, that's because of the difference. This has a negative sign associated with it. The d value has a positive sign. That means whenever you see a negative sign in a generic equation, whatever you are presented with, you put a circle around the constant and its sign and you flip it. Here, because of that positive sign, we put a circle around the constant and its sign and we keep it as is. Let's now look at the parent function. Recall, the parent function is going to be y equals log of x, and that of course has a base 10. The parent function is going to have a vertical asymptote at x equals 0. It's going to have a point at 1 over the base, comma, negative 1, a point at 1, comma, 0, and a point at the base, comma, positive 1. Okay, let's go ahead and transform each of these sequentially. Let's start with the vertical asymptote. Originally, x equals 0. Our x prime is going to equal x over the b value minus c. Our x prime, therefore, is going to be 0 over 1/3 plus 3. X equals 3 is our new vertical asymptote. Our first point, the original point, is going to be 1 over the base, comma, negative 1. Our x prime is going to be the original x over the b value, which is 1/3, plus 3. 1/10 divided by 1/3 is the same as, if you use keep change flip, 1/10 times 3 over 1, which equals 3 over 10. We're going to add 3 to that. That is 3 over 10 plus 30 over 10, and that gives us 33 over 10 for our new x value. When you divide by a power of 10, our number is going to get smaller. So let's put 33 with its original decimal point, and let's put zeros on both sides. Because we're getting smaller, whenever you're dividing by 10, this number is going to get smaller. That means we're going to be moving the decimal place to the left. How many places we move it is predicated on how many zeros associated with the power of 10. So here, we're going to move it one place to the left, thus making this number smaller. So that is our new x value. Our new y value is going to equal a times y plus d. Our original value is, y value is -1, and our a value is 3. So we're going to have 3 times -1 plus 2. And that's going to give us -3 plus 2, or -1. So our first point is going to be 3.3 comma -1. Okay, our second point, we're going to be working with 1, 0. X prime is going to equal 1 divided by 1/3 plus 3, and this will evaluate to 6. Our y prime is going to be 3 times 0 plus 2, and that evaluates to 2. So our second point is going to be 6 comma 2. Our third point, we're going to start with the base comma 1. Our new x prime is going to equal the original x divided by 1/3 plus 3. That's going to be 33. Our y value is going to be 3 times 1 plus 2, which equals 5. Okay, here are our 3 points, and we have a vertical asymptote of +3. Let's go ahead and graph this. Here's our vertical asymptote at +3. See, our first point is 3.3 minus 1. Next point is 6 comma 2, brings us about right here. And finally, 33 comma 5 would be something like this. So we're going to have a graph that hugs the vertical asymptote and heads towards quadrant 1. Let's see if quadrant 1 fits our intuition. If we go back to the original equation, we see that there is a positive sign associated with the y value and a positive sign associated with the x value. So 2 positives does indeed give us quadrant 1, and this is our final graph. Let's go ahead and test this on Desmos, which is our graphing calculator. Here is the original equation. We do have a vertical asymptote at x equals 3, and here are our 2 points, 6 comma 2, 33.5. I guess I forgot to plot the first point, which was 3.3, -1, but you can see that that does fit the graph.